All right, so I'll go ahead and begin. We may still have a few people showing up, and my colleague Kelly Peretz will let them in as they come. Um, oops, hold on. Someone just took control of my presentation. Let me go find that again. Let's see. All right. And I think
We can see it again now, Gail.
all right, awesome. So just making sure I don't need to change any settings here. Make sure nothing weird happens. All right. So this is our webinar on REL61. REL61 is an alloy we produced a few years ago now, but it's been having a lot of success. And we kind of want to shout from the rooftops at how innovative and useful this could be to your production lines. So my name is Gail Tao, and I've been with AIM for almost 2 years now. And my background is in math and physics, and I used to actually teach college students. And then I did a lot of writing and creative writing, and then that morphed into technical content writing. And now I'm at AIM giving webinars and learning all about solder so I can tell everyone all about our products and what we're innovating these days. So just a little overview. We'll start with just a very brief introduction to AIM. Many of you probably are already familiar with us since you're here. An overview of the REL61 alloy and some of its key features and benefits. We're going to go through we have a ton of internal and third-party test results on this alloy, showing how good its performance is. And we're going to go through just some of that. And then we're going to cover how it compares to some common alloys, SAC305 and SN100C, for example. We'll give a little overview of just some of the success stories customers have had with this alloy recently, and then we'll summarize and wrap it up at the end. So AIM solder, AIM has been around for many, many, many decades. Started as American Iron Metal, a sort of metals recycling company. And then AIM Solder is a subsidiary of that. We supply solder paste, bar solder, wire solder, flux cleaners, adhesives, underfill, ribbon, foil, for electronics manufacturing and for industrial applications all around the world. We also offer, we say we're a cradle to grave supplier in North America and other parts of the world. We also recycle dross and scrap and recover the metals from that as well. So this is just, this map might be, I can't remember if this is our newest one or an older one, but we're all over the world. We're located in many countries, and we have, I think, 10-ish manufacturing sites. So we're able to ship locally to places without necessarily crossing borders, which could be tricky. Yeah, we've been around. We're everywhere. We're established, and we also have, we sort of brand ourselves as being not just solder suppliers, but solder supporters. We have a lot of technical support services that we like to help people out with. And that can be everything from solder joint analysis, solder pod analysis, helping you with reclaim, consulting, technical training, seminars. We have lab services. We can help you figure out what's going wrong in your process. We have technical support engineers that will go on site, answer your questions around the clock. So we know solder, especially in electronics manufacturing, it's not just getting the product that's important. It's getting that process optimized. That's a really big part of your success. So we always try to couple the two. We don't want to just give you a product. We support the product we give you. So here's sort of a brief overview of REL61. I kind of want to start off with an understanding of where it sits in the evolution of alloys. So many of you may know back in the day, tin lead was all that solder was. Tin lead was the go-to alloy. But then there was the move to lead-free. So people were trying to figure out how can we make a solder alloy that performs as well as tin lead without the lead. Well, we're still working on that, right? The first generation alloys that sort of came out of this, the leader of the pack was our standard SAC305. That's the tin, silver, copper. And it worked fairly well. It was not as good, still is not as good as tin lead, but it was compatible with existing processes and leaded components. It tends to be higher in cost. It doesn't have the greatest mechanical properties. It can have poor aging performances. There's a lot of drawbacks to it, but there's also a lot of situations where it worked well enough that that sort of became the first generation standard. People always try to improve upon things. We want stronger, more reliable alloys. In comes the second generation. So instead of just SAC305, which is that 3% silver, 0.5% copper, people played around with different percentages of silver and copper. Lowering the silver content lowers the cost, which can be helpful, but it tends to make things a little less reliable. It's still compatible with lead. Another alloy that came out of this was SN100C, which is basically almost 100% tin with a few little elements added in there. And it tended to perform fairly well, reduce defects, improved joint strength, but it has a higher melting temperature. So tin lead has a lower melting temp than a lot of our modern solder alloys. And part of what people try to do is they're trying to get back to that lower melting temp. But usually when you do that, you start sacrificing a lot of reliability and other things. But lower melting temperatures can be nice for production because, well, lower energy costs, but you're also less likely to damage your components and your substrate and all of that. So SN100C tended to outperform SAC305 and some of the SAC alloys in certain situations, but it's also a higher melting temperature. It became widely adopted in wave soldering applications, less in surface mount, but because of that melting temperature. Then we move on to the third generation of lead-free alloys, and that's where REL61 lives. So REL61, it's essentially like you take your standard SAC305 or SAC alloy, you take out some of the silver, not all of it, but I think about 4/5 of it from SAC305, and you add in some bismuth. And that does a few things to the alloy. So bismuth is kind of an interesting metal because if you put a lot of it in, you can get a nice low temp alloy that melts at a much lower temperature, but tends to be not nearly as reliable as the SAC alloys. But if you add it in just a few percentage, smaller percents, it actually enhances the overall performance of the alloy. So it's sort of paradoxical in a way. Bismuth has this reputation for being brittle, but in smaller percentages, it improves hardness, it can enhance the strength, it improves aging performance, and all sorts of other features of the alloy. So REL61 was essentially we take SAC305, we take out some of the silver, we put in some bismuth, do some other minor adjustments. And what we get is a really great performing alloy in the same space that SAC305 and those types of alloys perform in. It has a slightly lower melting point than SAC305, enhanced strength and performance, reduced tin whiskers. We'll talk about those a little bit later. Really good aging performance. And we've got some really great pictures to show with that. The one drawback is that it's not compatible with lead. And that's because when bismuth mixes with lead, you get a really low melting combination and your reliability goes down the drain. So this came up in our third generation lead-free and not in the first generation, because first generation lead-free, we still have a lot of lead components coming through the production lines. A lot of times we're doing this lead-free soldering with lead still in the process. but most places nowadays, after they've made that transition, they're not seeing any lead components or lead materials coming through their process, so you don't have to worry about that mix anymore. And if you're to that point, switching to REL61 from something like SAC305 can make an awful lot of sense. The lower silver content lowers the price by a lot. Slightly lower melting point is just generally beneficial. It's lower energy use. You get to save on board damaging components and so on. And it tends to have better strength and performance across most metrics. So that's one thing you're going to hear me saying again and again is if you're comparing REL61 to something like SAC305, you're saving money and you're performing better. So it's kind of a win-win. It's like, why would you not go with that? And really the only reason to not go with that would be if you have lead in your process. And so that's sort of where REL61 sits in this evolution of alloys. So just a brief summary, it's a low-cost SAC305 alternative. So it has really good reliability compared to low and no silver alloys. I should mention it is not the same as a high reliability alloy. That's our REL22 alloy that's made for the highest reliability applications. That's our one that really competes with tin lead in performance. REL61 was really designed to be a SAC305 alternative. It's very cost effective and it performs better in the same places SAC305 is commonly used. Really good wetting performance, tends to be reduced voiding, higher strength and hardness. In wave soldering and selective applications, you get really good barrel fill and so on. And a lot of those features are a direct result of the few percent bismuth in the alloy. We actually have a paper out in, I think it's CircuitNet this month, that talks about adding bismuth to SAC alloys and so how if you have a low temp alloy that's got, you know, half of its bismuth, then you're getting that brittleness and all of those sort of negative bismuth features in exchange for that lower temperature. But when you add it in a few percent, it tends to improve performance across most metrics. And that's sort of what's going on with our REL61. All right, so here's just a direct comparison of some of the physical and mechanical properties of REL61 with SAC305. So you can see melting range, it's melting about 10 degrees, 5 to 10 degrees cooler in Celsius. Density is pretty much the same. Wetting performance is fairly similar. It has improved hardness. And then the other really interesting one is the tensile strength after aging. So we have some pictures of this later in the presentation, but when these alloys were cast and then aged at 150 Celsius for 24 hours, we see REL61's strength pretty much stays the same, but SAC305 and a lot of other alloys, their performance goes downhill very fast. And so that's a very big distinction between REL61 and many of the SAC alloys. Cost reduction is a huge motivator for people adopting this alloy. So again, depending upon what the metals markets are doing on any particular day, 10 to 20% cost savings, okay? I was just looking up metals prices this morning, and silver costs currently about 60 times what bismuth costs per pound. And so you reduce a few percent silver and you replace that with bismuth, and that leads to the significant cost difference in this alloy. So it performs, again, really well across pretty much any soldering application. So the nice thing about REL61 is you can use it in your SMT line. You can get it in wire solder. You can get it in bar solder for your wave pot. It works really well in selective soldering. So you can use it essentially across all production modes. And in SMT, the slightly lower reflow temperature sometimes will help with your process. Again, you're not cooking your boards as much as you were with other alloys. Really great print transfer efficiency, improved wetting, really well-formed joints with this alloy. And it doesn't degrade after thermal aging. So the picture at the bottom here shows microstructure of SAC305 and REL61 when they're initially cast. and then after aging at that 150 Celsius for a day. And what you see is the SAC305 forms all of these sort of structures within it, and those can lead to paths for breakage and reduced structural integrity. REL61, in contrast, tends to maintain most of its structure even after the aging. Uh, and again, with selective and wave soldering, it works really, really well. We sometimes have people ask, does it contain phosphorus, which is used to reduce dross? It does not. Many bar solders contain trace amounts of phosphorus to reduce dross, but REL61, possibly due to that bismuth content again, dross is less. Selective soldering nozzles degrade really fast with phosphorus. There's a picture example here, but REL61 doesn't have that in it, so you don't end up with that issue. Selective soldering is also known for getting worse barrel fill than wave soldering, but REL61 seems to have really great barrel fill with wave and selective applications. So again, that might be the bismuth content contributing to some of its ability to flow well when it's in molten form. Sometimes people ask about compatibility. Is the REL61 alloy compatible with other things we're using? And so REL61 is essentially a low silver SAC with a little bit of bismuth, okay? So it's essentially compatible with anything that SAC is compatible with, as long as bismuth is fine in the situation. So most elements in lead-free environments are fine with it. That includes SAC alloys, nickel finishes, trace germanium. The only thing it's really not compatible with is anything with lead. And that was because, again, the bismuth will combine with the lead and create a really low melting eutectic and cause all sorts of problems. But if you have lead out of your process and you've been using SAC for years, that's might be a really good time to think about REL61. If you're not worried about lead anymore, you're going to save costs. And again, as we're going to see again and again in this presentation, the performance actually improves. So there's very few times in manufacturing when you reduce costs while your performance goes up, right? It's usually, you have to sort of weigh the pros and cons of, well, we're going to save money, but we're going to have to worry about this thing now. With REL61, as long as lead is out of your process, that really isn't the case. There's not much of a trade-off here. So now I'm just going to go through a lot of test results, and this is only a subset of some of the stuff we have on this alloy. So this alloy, I think we first released it in around 2015. And in the years since then, many, many customers have adopted it, and we just have success story after success story. People really like this alloy. So this is just some of the test results. Here we're looking at kinetics of intermetallic growth. It tends to reduce the IMC layers a little bit, which can improve solder joint durability under thermal stress. So here it is just in comparison to SAC305 and a tin copper nickel alloy. Wetting comparisons. So in some of our studies, we see similar types of wetting performance depending upon what we're measuring. But here we're looking at the sessile drop test, which measures, so essentially you're measuring the angle of your drop, and a smaller angle indicates better wetting. And when we compare REL61 to SAC305 to a tin copper nickel alloy, REL61 has the lower contact angle, which tends to correspond to better wetting. This is again a wetting comparison. The graph on the right just shows the wetting force with respect to time. REL61 tracks right along with SAC305 on this graph, so very similar wetting balance performance. And then visual appearance, we'll see more images of this. REL61 kind of has this dull but uniform appearance compared to SAC305 being shinier. Sometimes people get worried about that. They're used to alloys being super shiny once they're soldered. REL61 has a matte finish, and that again is just due to the composition. It's supposed to look like that. And there's actually some benefits to looking at like that. Anyone who uses automated optical inspection equipment knows that shininess means reflections, means light shining off of multiple surfaces, means interference with your data. Well, REL61 is nice and dull, and it doesn't do that. So we've had a lot of customers who've had issues with their automated inspection, getting too many false negatives, switch to REL61, and that isn't happening anymore. We actually did a study we presented at SMTAI this year on the shininess essentially and how that looks in AOI machines. And we'll see some pictures from that a little bit later on. This is a tensile creep graph. So in an age condition, the performance of REL61 was better than SAC305. So the red is SAC305, the green is REL61. And you see over time, REL61 tends to remain nice and stable. This is my favorite one. This is the tensile strength as cast and after aging. And there's such a stark difference here between REL61, SAC305, and many of these other sort of SAC alloys in SN100C. So we first cast all of these different alloys and we measure the tensile strength. And we see REL61 as being one of the winners. SAC305 gives the same tensile strength. They look equally strong when you first cast them. But then you age them for a day at 150 Celsius. And what happens? REL61 goes from a tensile strength of 75 down to 70, barely a drop. SAC305, on the other hand, let me get my laser pointer out here. SAC305, which started at 75, essentially cuts in half. And all the other alloys in this test we see drop rather significantly in aging. And you can see this represented on the graph here. The blue is as cast and the red is after aging. REL61 keeps its strength. Everything else, even if it started strong, drops significantly. So it has really good aging performance compared to a lot of these alloys. Hardness test, so REL61 is significantly harder than some of these alloys, has about twice the hardness of SAC305 and the tin copper nickel. We've done thermal cycle testing with this alloy. So this is compared with SAC305. These are 3 different components we did measurements on. In this case, the line where SAC305 is, which is the lighter color, is sort of our baseline, and this is how REL61 compared to SAC305 in performance. So it outperformed on the LED component, on the MLF component, and was similar on the resistor component. And this is, again, this was third-party test data. These are the results they got. So thermal cycle testing, depending upon the component, it was equal or better than SAC305. This is thermal shock performance. So REL61's thermal shock performance, it approximately doubled the lifetime of an assembly versus SAC305. We look, so thermal shock it's like thermal cycling, but you make the temperature change a lot faster. And here we see after 1,500 cycles, there's essentially no REL61 failures, but we've got quite a few SAC305 failures. And then we start seeing some REL61 failures when we're getting to 2,250 to 3,000 and so on, but it's still massively outperforming SAC305. This is more thermal shock test data, just with different components. And again, we're seeing the same results. SAC305, which is the red bars, starts failing faster and fails a lot more than REL61 does. REL61 lasts quite a bit longer. This is a vibration test. So here we see, shake it and see if you can break it. And again, REL61's failure rates initially were lower. Later on, they sort of even out though. So in this particular test, we're seeing somewhat comparable results between the REL61 and the SAC305. This was a drop shock test. So again, drop it, see how long it takes to break it. And what we're seeing is, so we had multiple alloys in this test. REL22, I mentioned before, that's our high reliability alloy. Different than REL61, has a few other elements in it. It's pricier, but it's our top performing if you need the absolute most robust alloy. So it won. not surprisingly, right? But REL61 performed better than SAC305, and then REL61 and REL22 were both less variable in their performance on this test. Tin whiskers are something that happens sometimes with SAC or other tin-based or alloys, SAC alloys. Essentially, you put some stress and strain on something that has tin, and these little whiskers start sprouting up. And that's a problem, obviously, because that can create conductive paths that you don't want to be there. So one thing we've noticed is, for whatever reason, probably due to the bismuth content, it somehow mitigates the tin whisker growth. We performed this test. We had these coated wires with these two alloys. We bend them, we stress them, and we look for tin whiskers. SAC305 has them, REL61 does not. So if that's a concern in your production, rest assured, REL61 doesn't seem to have that problem at all. And we may even be doing some additional studies on this in the future just to sort of understand it better and look for situations where people are having issues with tin whiskers because they moved away from tin lead, and now they're need to get rid of that. Well, the bismuth content in REL61, for whatever reason, seems to make that go away. We have the same type of thing happens in our REL22 alloy, that high reliability alloy as well. Voiding, always a concern. Again, what causes voids is many, many different things. Some of it's process control, some of it's the flux medium, and some of it might be the alloy. And REL61, again, that bismuth content, and there have been some other papers I've seen by other people that have shown that it seems to contribute to reduced voiding. And so, oh, we got a question popping up here. Let's see what this says. I do not think so. I do not. So someone is asking if REL61 has a military spec approval, and which spec approvals does it have? That is something I don't know about off the top of my head. I don't know if any of my colleagues are on this meeting and might happen to have that knowledge, but I can look into that.
It doesn't.
It
that I'm
doesn't.
aware of.
Okay. Yeah. Yeah. Yet, right? That's what I like to say. Yet. But yeah, lower voiding. So you want to get rid of voiding. Some of that might be the alloy. So your process, your flux medium, and your alloy can all contribute to that. Print performance, again, this may be more flux medium sometimes than alloy, but our REL61 with the standard flux mediums we offered and seems to have very good print transfer efficiency, very good print performance, even on fine feature devices. So we're going to look a little more closely at the whole shininess aspect. So here's just a nice little picture of a little drop of solder after it was melted and solidified. And we see REL61 has that sort of matte, dull, uniform finish. SAC305 has shiny spots and dull spots. So what does that mean? This is just another picture sort of showing that. REL61, nice uniform matte finish, and SAC305, shiny spots. Okay. Now, in terms of performance, that doesn't really tell us anything, but it does tell us something about what our inspection equipment is going to see. So we worked with Omron recently and one of their sort of high-end inspection machines to see what these alloys look like after reflow under their inspection equipment. This particular equipment sort of shines different colored lights at different angles. So when you see greater differences in color gradients and shinier spots, that's telling you you're getting a lot more variation in the surface, you're getting a lot more reflection in certain places, and that can make it harder for the machine to read. And depending upon what machine you have, so this particular machine was sort of top of the line 3D image creating machine. If you got a 2D machine or something that's really just relying on nice reflected light shown at a specific angle, then you're going to get a lot more noise in the system. So when we look at the SAC305, we're seeing some really bright spots. We're seeing much more dramatic color changes versus the more uniform appearance under the inspection with the REL61. This one really shows the difference. So this was sort of a window pane print pattern. And under the inspection equipment, what it looks like with SAC305, you've got very dark spots, very bright spots, and some more significant color gradients versus the much more uniform light reflection of REL61. The person we worked with said, it took a lot longer to train the machine how to recognize things with SAC305 because of the variation. With high-end equipment, you can usually compensate for these differences without too much of an issue other than the initial setup. But with other equipment or older equipment, that difference in reflection can be a huge difference in your production line throughput. You have a lot of shininess on your board and you can get a lot of false positives. That's a huge thing with AOI machines. Like they tend to spit out significantly more false calls than actual calls. And reducing that reduces your production, reduces your production time. You increases your throughput essentially. This is just another picture. This was a print pattern that was a spread test on the board. And again, you can just see dark and light on the SAC305 versus much more uniform results with the REL61. Let's see. I'm going to mute whoever's typing furiously over there. All right. Okay, through-hole reliability. So that's another big one, right? So again, REL61, you can use it for SMT. You can use it for wave and selective soldering. And yeah, so how well does it perform with through-hole reliability? So it performs very, very well. Again, it tends to have very good barrel fill. It has very good strength compared to SAC305. This was some of the results of a test, a thermal cycling test for between -20 and 100 Celsius, looking at SAC305 compared to SN100C, or sorry, REL61, SAC305, SN100C, and tin copper. This is a little hard to read, but this is sort of describing the thermal shock in the cycles, or thermal cycles really, and how the test was run. But here's the real rub. These are the results. So 0 hours, no failures. 750 cycles, we're starting to see failures with the tin copper and the SN100C. At 1500 cycles, we start seeing failures with SAC305. At 2000 cycles, REL61 is still holding strong and it's beating out on all of them. It has this beautifully formed fillet, great hole fill, really good joints formed. Again, the barrel fill of REL61 tends to be better than a lot of these other low silver alloys in SAC305. We've had many, many customers that have had issues with barrel fill in their wave or their selective, switch to SAC305 or switch to REL61 and it goes away. They start getting 100% barrel fill on everything. The other nice thing is if you are sort of going from a lead-free wave to REL61, you can make that transition without needing a pot wash. So this was just an example of switching over the pot from one alloy over to REL61. We have a lot of people ask about dross. So you run a wave solder pot, you're going to have dross, and you don't want dross. And again, we talked earlier, that's why some of these alloys will contain phosphorus to mitigate that. REL61 doesn't have any phosphorus in it, doesn't have any added in our bar, because it doesn't need it. It naturally drosses less. So we had done a dross study where we melted each of these alloys under identical conditions, stirred them up under identical conditions, and saw how much dross formed over a period of time. And the winner was REL22. Again, that was our super high reliability alloy. Coming in second place is REL61, outperforming all of these other alloys, SAC305, SN100C, 0307, and so on. So if dross is a concern, which it often is, especially if you're considering a new alloy in your wave pot, rest assured, REL61 is going to improve results there as well. So these are just some simple, quick summary comparisons of how this alloy performs versus other common alloys in its category. So versus SAC305, again, it just performs it on almost everything. It costs less, it's harder, it performs better in thermal cycling. The intermetallic growth is slightly reduced, which improves its durability under stress. Wetting performance is a little bit better. Tensile strength as cast is similar, but after aging, REL61 is better. It has that dull sheen, which again, people unfamiliar with dull looking alloys might be frightened by at first, but that's just the nature of this particular alloy, and it actually works in its favor when it comes to inspection. Thermal shock, it outperforms SAC305. Vibration test, the results were somewhat similar on that. Hole fill, it outperforms SAC305, and with dross, it drosses less than SAC305. So again, I mean, making a switch can be a big undertaking, but if you're trying to save costs and you don't want to sacrifice anything, REL61 is really the way to go because your performance actually goes up while your costs go down. Compared to SN100C, so remember SN100C was sort of our second generation lead-free alloy. It tends to have that higher melting temp, which makes it more favorable for wave solder applications, less so in surface mount, though people do use it there as well. The costs are somewhat comparable because SN100C also doesn't have that silver content in it, which drives the price up. REL61 is harder, performs a little bit better in thermal cycling. Intermetallic growth can be somewhat similar. Wetting performance, REL61's better. That tensile strength, and after aging, it was better. Thermal shock and vibration can be somewhat similar between these two, but REL61 then does better with hole fill and also with drossing. So even compared to SN100C, which is similar price point, you're still getting better performance across a lot of these metrics. SAC307, that's sort of a low silver SAC alloy people tried to reduce costs with. Again, REL61 has similar pricing to SAC307, but REL61 outperforms it. So SAC307 is basically your SAC alloy with less silver in it, so it performs a little less better than SAC305. REL61 is your SAC alloy with less silver, but then we add in some bismuth, and then we improve our performance across pretty much every metric. So next, I'm just going to run through a few success stories. So this is just a small subset of some examples where customers tried REL61 for something and it worked out well. So in this first case, we had a manufacturer was wanting to consolidate their solder paste supply with AIM, and they needed to make the case to one of their customers who was using a competitor's SAC305 to switch to REL61. So M8 REL61, M8 is our flux medium. So they tried that with the same application, and they wanted to show their customer that it was going to be cost saving, superior performance. Other issues they were having with the incumbent paste, they had a lot of flux residue. Obviously, that's not alloy related, but our flux medium performed well there. And that was causing some problems with their testing. So our technical engineers supported an evaluation of M8 REL61, and it was within the limits of, we just used the standard incumbent reflow profile. End results were no issues observed. Post reflow, the joints met all the standards they needed to. Minimal flux residue, AOI inspection found no defects, and overall it seemed to perform better. Again, used our M8 solder paste with the REL61 alloy and the help of our technical support. Drove costs down. Further, we're able to consolidate with a single supplier, which makes life easier. Reduced flux residue. That's not an alloy thing, but it was the paste thing. And then wetting and printing were somewhat improved. So really easy to convince that customer to make the switch when you're able to show not only does the cost go down, but the performance went up. Another example, there was a new project with complex high thermal mass boards. So they previously had positive experience with our REL61 paste, and they wanted to see if it would work in this new product line with their end customer. It was very complex boards with high thermal mass in some spots, little differences in others. They evaluated the paste. It did require extending the reflow profile because of the thermal mass and the complexity. The end results were really good solder joints, a little bit of flux residue that didn't cause any issue. Voiding was minimal, and the paste performed well. The end customer approved the development of products with this paste, and it's in production. So again, our M8 solder paste REL61 alloy, they saved money. Voiding was minimal, and even though the board was complex, everything went smoothly. Another example, they were using a competitor SAC305, wanted to reduce voiding and eliminate solder balling. So they're trying to migrate from SAC305 to REL61 to save costs, but they also want to make sure performance issues get resolved in the process. They evaluated the paste. The incumbent paste they were using, a SAC305 T5 powder. We actually recommended just going back up to T4. Our T4 tends to print very well in some situations where people have used competitors' T5 paste, and there could be a cost difference there as well. The inspection data showed consistently good print performance. After reflow, everything looked beautiful. No solder balls were detected. Voiding went down. BTC and BGA voiding went down and outperformed the incumbent paste across most metrics. So we just had a question pop up on the couple questions pop up on the side. M8 paste, how does this compare to ultra low voiding paste? I think that's a it depends question. It really depends on what paste you're comparing it to. We've had a lot of people have really great success with M8. We don't really have a lot of voiding complaints on that paste. Is it called REL61 because of 6% bismuth and 1% silver? No, it has less than 1% silver and less than 6% bismuth. I can tell you that much. So why it's 61? If Tim is on this call, do you know the answer, Tim? You were probably around when it was named.
It's a long story. It doesn't have anything to do with the composition of the alloy.
Yeah.
It's more of a rev number.
Okay. Yeah, I've heard all sorts of interesting stories about our product naming methodologies. So maybe we'll just say it's top secret. All right, so again, this example, compared to the competitor SAC305, using the M8 paste, they saved money, voiding went down, the solder balling problem went away, and they had clearer residue with this particular M8 as a no clean paste than what they were using. Another example, again, it just improved printing and wetting, and it also reduced AOI false readings, which is something I had mentioned earlier, right? So they were having some trouble with their incumbent SAC305 paste. They were also getting dry joints, causing functional failures, and they were getting a lot of false calls on their AOI equipment. So they tried out our M8 REL61 and optimized the original profile temperature a little bit, and a little bit of playing around with the AOI program to reduce false passes, but the uniform matte finish also sort of contributed there. And the end result is everything improved. So the final success metrics, better wetting, better printing, reduced false calls, clearer residue. And again, you're saving money when you switch to REL61 from SAC305. So this was a selective soldering application. In this case, it was REL61 and our FX16 flux, which is designed for selective soldering and wave applications. They had poor hole fill on their bare copper bus bar. They had to touch up pretty much every joint after selective soldering, which, as you can imagine, really slows the production process down. So costs were going up, up, up. And they wanted help. What can we do about this? So we had a technical engineer help them out. They tried out the combinations of the incumbent SAC305 and REL61 with the incumbent flux and the FX16 flux. What performed better overall was the combination of REL61 and FX16. They got 100% whole fill. So they went from 100% touching up everything to 100% whole fill, which is a pretty dramatic improvement. The flux, our flux with the SAC305 did cause improvements as well, but that combo of the flux with our REL61 gave the best results overall. So again, touching up everything to touching up nothing is a pretty dramatic change. We got a couple more questions on the side. What thickness stencil is used in these comparisons? That I don't know. We have a lot of different examples and case studies and comparisons with different stencil thicknesses used. Peak reflow temperature. So I know the melt temperature of REL61 is about 5 to 10 degrees below SAC305. So you could theoretically set your peak reflow about that much lower as well. All right. Another example, this is, I believe, a wave soldering application. So they were using a SAC307 and I should say S100C. Didn't fix that typo. Customers experiencing a lot of dross in their wave line, and they wanted to see if REL61 would help their situation and also work with whole fill. So we gave them a REL61. And their engineering team gave it a shot. And in the end result, the X-ray inspection showed REL61 gave 100% vertical fill on all the through-hole components, better wetting, smoother looking joints than the SN100C. And dross performance is, again, dross is tricky because it really depends on your conditions of your test, right? It's not something you can just quantify across all situations. But we happen to know from our internal testing, it tends to dross less. And so again, they got improved wetting, perfect hole fill, smoother joints, reduced dross in this application. All right, another example. Again, improving barrel fill in wave and selective applications. So bridging an incomplete barrel fill, and they wanted to switch from a wave to a selective soldering application. The technical engineers assisted with adjusting fluxing program for improved flux, and then we validated REL61, fine-tuned the process, and until things improved. So after optimization, again, we're getting 100% barrel fill, and it eliminated bridging issues they were having. And with further adjustments, it performed very well. So there was a wide process window, which means there's wiggle room in there. So they were able to transition from a wave to a selective process for this. And again, sometimes going to selective means your whole fill goes down, but REL61 was able to get them 100% whole fill within a wide process window at that. So, summary. So I wanted to sort of give an overview of what REL61 is, and then also what it is not, so that you make informed decisions when switching to REL61. So what it is, it's a cost-effective SAC305 alternative. So you've got your next generation, third generation lead-free alloy, and it's going to cost less than SAC305, and it's going to perform better than SAC305. It's well performing. It outperforms SAC. It outperforms a lot of those low, no silver alloys that people try to switch to for cost savings. So again, it works really, really well in that space. It's versatile. It's phosphorus free. So you can use it in selective soldering. You can use it in wave soldering. You can use it in your SMT line. It comes in bar, wire, paste forms. You can use it in everything. It's lead-free compatible, so it's compatible with most elements in lead-free environments, including SAC alloys, nickel finishes, trace germanium, and so on. But what it is not is compatible with leaded alloys. That is the one caveat here. So if you have lead in your process, it may not be the right choice. The other thing it is not is we do not classify it as high reliability. It is better than SAC305 in reliability, but is not a, quote, high reliability alloy. That's our REL62 offering. And that one doesn't really save costs so much, but it does have the performance that rivals tin lead in many applications. So another question popping up on the side here. A lot of issues on selective soldering machines, soldering nickel finished surface of component leads. Using SAC307. Main defect is insufficient soldering or blowholes. Will REL61 improve it? I would say it very likely will. After this webinar, everyone who signed up should get a follow-up email, and it'll have contact button. You can contact your local sales rep, and they will be able to talk to you about that and connect you with our technical support team, who can also help you troubleshoot your problems and look at what a REL61 adoption in that process might do. So our key message that we want you all to leave this with: REL61 costs less than SAC305, and it's better than SAC305. So why would you not make the switch? Inertia is a big one. Lead in your applications, that could be a reason. If you need a high reliability alloy, we have that, that's REL22. But if you're just replacing SAC305, you're trying to save costs, you're having some of these wetting issues, you're having hole fill issues, REL61 might be the way to go. So let's see, it should hopefully you're using REL61 for 10 years. Which one are you selling more, SAC305 or REL61? I don't know the numbers off the top of my head, or Tim might have that info, but the other thing to consider is I don't know what those numbers would tell us, because anyone who's already dialed in their process for SAC305 and had that approval for everyone they're manufacturing for, people don't like to switch unless they have to. And so, you know, if the SAC305 numbers were higher, that might just be a sign that people haven't made the switch yet, because sometimes it takes a while. If the REL61 numbers are higher, then we can say, yes, everyone's moving to REL61. Why aren't you? So I guess that's my thought on that question. But SAC305, again, became popular because when we move away from lead, we need something that's still compatible with lead. And so until lead is completely out of your process, you're going to want to keep using SAC305 versus REL61. Once you're not dealing with lead anymore, there's really no reason to stick with SAC305. Something like REL61 is just going to save you money and perform better. But it's not always as simple as making the switch, because you have to convince your customers, you have to convince the end product people that that's what you need to do. You have to approve the process and so on. And sometimes people don't do that for whatever reason. We do say, again, we are solder plus support. If that is problem for you, if you are struggling with convincing people, if you are unsure of how to make the switch, we have technical support people who've done this a million times. So we are always happy to sort of help you figure that process out and make it happen. So at the end here, I have, I showed this one earlier. This is just a comparison of the mechanical and physical properties of REL61 with SAC305. Everyone who gets a follow-up email will get a PDF copy of this PowerPoint as well, so you'll be able to look at this more closely. But we also have the comparison with SN100C. So you can see how the physical, like the melting temperature is pretty different here and so on. Hardness values, how all of those properties compare. And then also a direct comparison with 0307. So, and beyond that, I just want to say, I think AIM Solder is a pretty great company. I've been with them for almost 2 years now, and I'm happy. They've been in the business of metals for 85 plus years. We're a global company. We have tech support and production and sales support all over the world. we pride ourselves on responsive support. We want you, if you are having a problem in your production line, we want you to be able to call us and you get a human right away who is going to help you right away, because time is money when your production line is down. We have a really strong R&D program. We're always trying to create the best products and the products you need for what's coming next in electronics manufacturing. And we really make efforts to have consistent quality no matter where we are. And sustainable solutions. That's why we have really robust recycling programs. So we'll give you dross reclaim buckets and you can ship those back to us and we'll give you a refund on the metals value contained within them and so on. So, all right, with that said, that is the end of the formal presentation. We have some more questions on the side here. Someone had asked sharing ATC results. Accelerated thermal cycling. Is that something we've seen?
Yes, so Gail abbreviated the thermal cycling results in the interest of time, but we have the data behind all of the thermal cycling test results that we generated. And in fact, if you're familiar with the ANSYS Sherlock reliability software, REL61 is part of that program. I don't use it. I'm not that familiar with it, but I know that it's part of that reliability prediction software. So the data that was generated to make REL61 data available in Sherlock is the data. That's the background. We have that background data. I think that.
Yeah, and then Dave Hillman just put in the comments that there's a really good paper we did in conjunction with Rockwell Collins where they tested, I think it was REL61, REL22, tin lead, and SAC305 and compared them with thermal cycling. And that was one of the graphs we had in here. Again, we have a lot of test data on this product. Our actual presentation that contains even more of it is like twice this length. But what was that?
Somebody was saying hi. I think somebody walked into somebody's office.
Oh, okay. All right. Any other questions before we wrap this up?
Yeah, great presentation, Gail. I just want to highlight the way that REL6 gotta mute that guy. REL61 was really developed as a low-cost alternative to SAC305 that addresses many of the issues that you might find with other low and no silver alloys. That was the purpose behind the development project. If you're familiar with SN100C, barrel fill on high thermal mass boards can be a big issue, difficult to overcome. REL61 resolves that issue. REL61 can be run at lower temperatures in some applications, which can be beneficial specifically in selective soldering, which I answered in the chat. It was meant to be equivalent to SAC305 in terms of in-process performance and reliability. And I think Gail's done a great job of demonstrating those advantages.
Yep. And then again, you'll all receive a follow-up email that'll make it really easy to contact someone from AIM if you want to learn more, ask some more questions, or try this product out. And you'll get a copy of this presentation as well.
Thank you. Excellent presentation. Thank you.
Well, thank you guys all for coming. It's really awesome to see so much interest in this product.
Thank you.
Thank you for sharing your valuable time.
Thank you.
Thanks, Gail.
Bye-bye. Thanks.
Thank you, Gail.
Bye-bye.
Excellent presentation.
Some snacks.
You're talking, but I don't.
So we're waiting just a few more minutes for people to show up.